Hello again, welcome to another video from Lockdown Electronics with me, Bill, and this time we're going to be looking at getting the most out of a single channel oscilloscope. Now there are plenty of bargain oscilloscopes going out there on eBay. Some are better than others, but you can certainly get a reasonably good scope for in some cases less than £50 here in the UK. And whilst some of them are double channel oscilloscopes and sometimes even more, quite a lot of them are single channel, and that is a bit of a limitation in one sense, but in another it allows you to actually use the advantages of a single channel scope to help you. So if that's all you've got, this video might be of some use. And today the scope in question is my trusty Hameg HM307, which is a 1970s oscilloscope. It's solid state circuitry, although of course it has a tube for the display, so it's got at least one vacuum tube, or valve as we call them here in the UK, in it. So let's go and have a look at what we're going to do. So in normal mode, as I guess you're probably familiar with, an oscilloscope produces its sweep waveform from internal circuits. The voltage from the probe is fed to the Y input, and the sweep waveform usually looks something like that: a ramp waveform moving the trace across the screen and then returning rapidly to the start point. The trigger point is usually at the start of that, although as you probably know, on some scopes you can adjust quite where the trigger point occurs. But the scope attempts to find a point to start the sweep, which then presents you with a synchronized display. The waveform appears to be stationary. The period of that sweep waveform is essentially equal to the time base of the oscilloscope, and that period is what allows us to make measurements against the graticule. So let's have a look how that waveform affects the scope's dot as it moves across the screen. Okay, so what you're looking at here is we've got the Hantek 2D72, which is a 2-channel oscilloscope, and we've got the Hameg HM307, which is a single channel scope but does have the facility to have an X input. Currently what you can see here is the channel 2 on the Hantek here is displaying a very slow ramp waveform. Currently there's nothing happening on channel 1. The Hameg is currently in its normal mode, in other words the time base is being triggered and the circuitry is looking for some kind of trigger, which doesn't exist because there's no input to the Y connection. So I'm going to put the scope into XY mode and I'm going to apply this waveform to the Y input, and if you now look what you can see there, as you can see I've now created a kind of artificial time base. So as the ramp wave climbs up, so the spot is moved to the right across the screen and it appears to start again. In actual fact what happens there is the very fast fall time means the spot appears to simply start again. In reality it's moving very quickly back across the screen and you just simply don't see it. So that's, if you like, just the X mode with no signal at all applied to the Y mode. When the scope's in XY mode, things are slightly different. The sweep is now controlled by the voltage that we choose to feed into the X input, and the Y input actually essentially is the same. It's the voltage which would usually come from the probe. So if we choose to feed in a ramp waveform, as you saw on the video earlier, we can get the sweep to cross the screen. And if we fed in an identical wave to the Y input, if you think about what that would produce, essentially as the dot moves across the screen, so the Y input would rise up as the voltage increases, and we would get a slope from bottom left to top right, and that occurs when the two inputs are in phase. If we so both X and Y input waveforms are in phase. If we keep the sweep waveform the same, but we reverse the waveform going into the Y input, I'll I'm sure you can probably deduce what that's going to do. As the sweep moves across the screen, so the pointer is going to go from high to low, and it will produce a slope like that. And in that case, the two waveforms are 180 degrees out of phase. So let's have a look at how that appears on an actual scope. Okay, so now we've still got the Hameg scope in conventional mode, but now we've got the Hantek scope listening to both channels 1 and 2. Channel 1 is the Y input for the Hameg, and the sawtooth or the ramp waveform you can see there is what's currently displayed on the screen. And I've got a similar frequency on channel 2, and I'm now going to switch the Hameg scope into XY mode so that we're going to apply this ramp waveform to the Y input, and we can see what happens to this display. And as you can see, you've got that sloping line as I was describing just now on the slide. Okay, so to illustrate a few Lissajous patterns, I've now got similar arrangement to before. So I've got channel 1, which is the Y input here, and channel 2 is the X input to the Hameg scope. So I've currently got a 10 kilohertz sine wave, and the yellow trace there is equal to the green trace there. So I'll put the Hameg scope into XY mode, and we get that characteristic sloping line. So if I start changing the frequency, and I'm going to change the frequency of channel 2, but what I'm going to first of all do is I'm going to set up the trigger mode on here so that the source is channel 1, and it is, that's fine. That just means that it'll start, the top trace will stay in synchro, which is helpful to view what's going on. So I'm going to increase the frequency on channel 2, and I'm going up in 100 Hertz steps actually. So straight away we get rather complex pattern on the Hameg scope, and as I step it up, and I'm just now coming up to, I've now doubled the frequency, so you get the characteristic double ellipse there. If I triple the frequency, we get that. If I go to 4 times the frequency, we're now getting that kind of pattern. So as you can see, there's a very distinctive set of patterns when the frequency difference, frequency is changing between channel 1 and channel 2. The other thing that's very useful from an XY point of view is that it allows you to view phase. So what I'm now going to do is I'm now going to change the phase of the second trace. So I'm going to start moving the channel 2 phase out of sync with channel 1, and again I'll do that in 10 degree steps. So that's 10 degrees out of phase. That's not particularly obvious on here, but if I go 90 degrees, it should now be very obvious to you. I'm now a quarter of the way along there, and get that very obvious ellipse waveform, and that shape would be independent of frequency. Let's go to 180, and we're now getting the right hand line again, as you saw earlier on the slide. And if we keep on going to 270, we're back to the ellipse shape, and that's identical to the one you saw at 90 degrees out of phase. And if I keep on advancing the waveform right up to 360, we're back to, we appear to be, well, we're back in phase again, so we've got that characteristic sloping line. Now that's a sine wave. Just take me a moment or two to change to a sawtooth waveform, and I'm going to do that on channel 2 as well. There we go. And now what I'm going to do is I'm going to show you what happens when we change the phase on a sawtooth waveform. And actually the same kind of things happen, but we get quite a nice sort of trapezoidal shape, so that's 90 degrees out of phase, a nice diamond shape. And if we continue till we're 180 degrees out of phase, we're back to that sloping right line, so that's exactly the same as the sine wave. If I advance to 270, we've got again the sawtooth waveform equivalent of the ellipse that we saw on the sine wave. And then if we continue forwards a whole 360 degrees, so we're back in phase, we appear to be back where we started, which in fact is exactly the case. So as you can see, even though this is a single channel scope, it does allow us to get some information about phase. So let's now have a look and see if there's a practical use for that in some circuitry. So what we're going to do is we're going to take a transformer, and we're going to attach a signal generator to the primary, and the secondary, in the case of this transformer, has got a centre tap. So we'll connect the centre tap to the oscilloscope ground, and we'll connect one of the outputs to the Y input of the scope and the other output to the X input. And as I'm sure you can probably work out, X and Y input waveforms will be 180 degrees out of phase. And practically that looks like that. So let's have a look how I wired it up. Okay, so here we've got my little home-built signal generator, and if you want to have a look at that, it's a kit that's actually quite useful. It's worth building. There's a link up the top, so you can click on that and see find out all about it. I've got that signal generator producing the waveform that I've asked it. Well, it's sort of a triangular-ish wave, and I've got that feeding into the primary of this transformer here, which is just a single coil primary, and the secondary has got a centre tap. So I've got the centre tap, which is the black wire here, connected to the earth for the oscilloscopes, and I've got the channel 1 of the Hantek and or the Y input of the Hameg connected there, and I've got the X input connected there. So let's just have a look at the results that we get on both scopes from that arrangement. Okay, so here we have a sawtooth waveform. It's been produced by one of my little kit-built signal generators, and I've currently got it feeding in conventional mode into the Hameg and into channel 1 on the Hantek scope, and as you can see they essentially agree with each other. If I just alter the time base a little bit, you'll see the waveform is pretty identical. Just a little bit bigger screen on the Hantek, it makes it just easier to see. And if I now go, so that's on the earth, that's on one side of the centre tap. If I now go to the opposite side of the centre tap, as you can see, we've got exactly the same waveform. So it doesn't, apart from the fact it tells us we have the same waveform, and there's yeah, it's identical. So let's now leave the Y input connected, and let's now connect the Y input connected to channel 1. Let's get the X input connected to channel 2, and straight away we can see that those signals are actually out of phase, 180 degrees out of phase in fact, which is exactly what you'd expect picking up either side of the centre tap on a transformer. And that's not evident at all on the single channel scope. But let's now go into XY mode, because we're going to see no prizes for working out. It's going to be a sort of a sloping line. Is it going to be sloping bottom right to top left because it's 180 degrees out of phase? I rather think it is. And there you go. Got just a very slight ellipse there, but essentially that's telling us pretty clearly, those two waveforms are 180 degrees out of phase. So it is possible to get information from both channels on a single channel scope. Sure, it's a great deal easier when you can see both on there, but if this is all you've got, actually this can tell you a little bit more than you might first imagine. Okay, well that's it for another video. In conclusion, I think it's worth pointing out that single channel scopes have got a little bit more to offer than you might first imagine. So if it's something you've been offered or something you've spotted, I would suggest go for it. One of the great things about an older instrument that's pretty much fully manual, a little bit like my Hameg scope, is that it really forces you to think about what's going on, particularly when you plug a probe in and the display appears to be blank, maybe because the signal is somewhere up there or somewhere down there or whatever, and it really makes you think about what you're doing. So it is quite a good learning tool, and certainly my scope has helped me in that sense. Hope that's been useful. Thanks very much for watching. If you've liked it, please click the thumbs up. If not, you can click the thumbs down. Either way, still appreciate it. Be great if you could subscribe, and look forward to seeing you on the next video. Thank you.